essential. When you guys see rational functions, I think you should be using different strategies to graph these beyond the calculus. I would just use what you already know about asymptotes and plot a few points. Now, for other functions, it's going to actually be really helpful to use the calculus. Here's an example. You probably aren't super familiar with this graph. I mean, this looks like a line right here, and we know like square root functions in general look like this, but we've got some oddities happening in here with the way that the x is and everything. But when you're multiplying together, what does that mean? You're probably not familiar enough with graphs to have a really good idea about this, which I totally understand. So I'm going to go ahead and solve this by using some calculus and see what I can find out. I'm also going to use some other key features like y-intercepts and x-intercepts because that can be helpful too. In fact, maybe I'll even start with some of that. Y-intercepts are going to occur when you have an input of 0. If I have an input of 0, I get 0 times other numbers times the square root of 4, which is 0. So my y-intercept is at 0. This is already in what we would call factored form, and each one of these solutions would give us our x-intercepts, which one's at 0, which matches what we found with the y-intercept, and the other's at 4. So yay, I have 2 points. I've got 2 points. I'm going to use calculus to find the remaining points and figure out what this curve looks like. So I'm going to start by taking a look at my first derivative. At the first derivative, it might be helpful to rewrite the function g with a rational power here instead of a square root symbol. So I'm going to use the product rule in order to find the first derivative. So I'll do the first times the derivative of the second times the chain rule, because I had a function within a function, plus the second times the derivative of the first. Now ultimately what I'd like to do is get this all in factored form on the right hand side, and I'll set this equal to 0, because what that will do is that will allow me to find my critical values. So let's see, the 1/2 and the 2 are going to go ahead and cancel out. And I might notice here that I have this common base here. And I'm going to factor out that common base to the lowest power that is present here. So I'm going to factor that out as 4 minus x to the power of negative 1/2. And what I have left from the first portion of this, prior to the plus sign, I have the x and the negative 1. I might choose later to factor a negative out. Sometimes that's helpful, maybe not. There's a little bit of choice there on your part. And then I have this 2 right here. And then this expression 4 minus x to the power of 1/2, I have one of those left. If you're having a little trouble with that, try distributing back. A power of negative 1/2 and a power of 1 would add back to that positive power of 1/2. And so now I'm just going to simplify this. So I have a portion that would need to be on the denominator. And then on the numerator, if I do a little combining like terms, let's see, this would be 8 minus 2x. So I've combined with another x, 8 minus 3x. Remember, your first derivative is going to allow you to see where are the critical values. So we have critical values coming from both the numerator and the denominator. The solutions of the numerator and the denominator are going to be your critical values. One of them is at 8/3. Maybe like, where'd you get that? I took that numerator and set it equal to 0 and solved that real quickly. And then my other critical value is at 4, which is a little easier to see on that denominator. Now at 4, this critical value is where the derivative is undefined. But remember, the derivative being equal to 0 or undefined will give you locations of critical values. And those critical values are possible points of inflection. And those are possible relative extrema, or relative extrema if you prefer that type of language. So I also want to look at the second derivative. And the second derivative is a little bit more painful, but it will help me see where my possible points of inflection are. And so I'm going to write my second derivative back from this form's a little bit more useful for my first derivative. I have 4 minus x to the negative 1/4 It's kind of up to you if you want r to the negative 1/2, and this is 8 minus 3x. If you wanted, you could think of this as a quotient. Use quotient rule. I'm going to use product rule again, just because I find it to be a little bit easier. I tend to make a little bit fewer mistakes, but it's really up to you. All right, second derivative. I will do the first expression, first function, times the derivative of the second, plus the second, times the derivative of the first. Be careful here. I'm going to use power rule, followed by chain rule. Sometimes people miss that -1, but you have to take the derivative of the inner function. So if I then set this equal to 0, I'm going to go ahead and factor out the common factors. Both sides have this base of 4 minus x. I would like to take that out to the smaller power. I do have also some negatives and things that will cancel out. Now, I have this 1/2. This 1/2 needs to be factored out. Now, the sign itself of that 1/2, no big deal. It's going to cancel with this negative right here. But I cannot leave that 1/2 inside the interior. I need to factor it out. And so it might be helpful for me to think of this -3 over here as -6 over 2. And just get a common denominator to help me as I factor it out. You might find it to be a little bit easier to do that. That was -3. -6 over 2 would be an equivalent version of that. Okay, so I'm going to factor out the 4 minus x to the smaller power of -3/2. I'm also going to factor out this 1/2. So basically I have this 4 minus x to the power of 1. If you distribute back and you combine those powers, you will get back to the power of -1/2. I already took out the denominator of -2, so this -6 is still here multiplying that. I don't know. I kind of like it in the front so I can remember to distribute it. The power of 1 is there, but I'm not going to write it. Let's see. This negative and this negative canceled out. The 1/2 factored out. This yellow portion factored out. So all I have left is the expression 8 minus 3x. So if I then simplify this, on the denominator I have the 1/2, the 4 minus x to the positive power of 3/2. And then on the numerator, let's see, I have a -24 minus 6x plus 8 and minus, oh, sorry, this is a plus 6x, and then minus 3x. So that would be 3x, looks like minus 16. So my possible points of inflection would be at that numerator's solution, which is positive 16 over 3. You could set that equal to 0. Or at the denominator's domain restriction of 4. Because remember, just like critical values, points of inflection can also occur where that second derivative is equal to 0 or undefined. Either one would give you possible points of inflection. Now, critical values are not necessarily extrema. And possible points of inflection that we find here from the second derivative are not for sure points of inflection. We've got to look for sign changes. And so what I'm going to do is I'm going to make this kind of modified table here, what Earl would call an alt table. And I'm going to put together my critical values and my possible points of inflection all in one table to try to get a big picture of what's happening with the function g. So I want to really look at all of the different ranges of values that we have. So I have 8/3, I have 3, and then I have, let's see, or 8/3 and 4 are kind of my points of interest, and 16/3. Okay, so those are my ones. So I'm going to go from -infinity to 8/3 because that's the smaller value, and then from 8/3 to 4. And then I would expect normally to go from 4 to 16/3. I'm actually not going to this time. Normally I would, want to make sure and go on both sides of those possible points of inflection, but this is a unique graph in that there's a domain restriction. Remember, we only are going to take we're only looking here at calculus with real values, not imaginary values, no imaginary outputs here for Calc 1. And so when I'm looking at this, I cannot put in values that are larger than 4 into this expression, otherwise I'm going to get a negative underneath that square root. So actually, I have to stop at 4. So it's interesting that I got that value of 16/3, but graphically it doesn't mean anything. So weird. So we still have to make sure we're thinking about things, and domain restrictions are important. So I'm actually only going to be really interested in 2 intervals, to the left of 8/3 and to the right of 8/3 up to 4. And I'm interested in what's happening with G prime and G double prime over those 2 intervals, because they're going to both give me information about G. So starting with G prime, if I pick a number in between negative infinity and 8/3, such as 0, remember here's my expression for G prime when I simplified it. So let's see, if I substitute in, for example, a 0, all I really care about is the sign. On the numerator, I would get a positive. On the denominator, I would get a positive. And so the first derivative in this interval will be a positive. What that tells me is my function G is increasing on that interval. So from left to right, we're going uphill. We have positive slopes. If I pick something in between 8/3 and 4, maybe I'll pick 9/3 because that's an easy number. It's 3. On the numerator, I would get 8 minus 9. I'd get a negative. On the denominator, I would still get a positive. And so a negative divided by a positive is a negative. I anticipated that there should have been a sign change there. That's why it was a critical value. By the way, the reason 4 came up is because of that endpoint, that domain restriction. Something was happening. The derivative there will be undefined because it's an endpoint. Okay, and so then G would be decreasing from 8/3 to 4. All right, now if I take a look then at my second derivative, I am going to notice that my possible points of inflection are not going to be points of inflection. First of all, 16/3 is not even a point I get to test. It's outside my domain. So 16/3 for sure is not a point of inflection. 4 is the endpoint. An endpoint cannot be a point of inflection because points of inflection must have a sign change for the second derivative on the left and right side. We don't have a right side. So whatever value I get for the second derivative should be the same value for my entire interval from negative infinity to 4. And it's going to tell me the concavity. So I'll pick a number like 0. I would get, and now I'm looking at my second derivative. So when you're testing the point of inflection, make sure you're testing it in the second derivative here for concavity. So if I substitute in a 0, I get negative 16 over a positive 4 to the 3s power will still be a positive times 2 is still a positive. I have a positive or a negative divided by a positive. This is a negative, so I will be concave down. If I pick something just because I wanted to verify, I shouldn't have a sign change here, but if I want to verify, because my only possible sign changes would be at 16/3 or 4, which we're not actually going on the other side of 4. But if I wanted to check, I could plug in a 3. I would still get a negative on the top. I would still get a positive on the denominator. And I would still get a negative second derivative, which tells me that my graph is concave down. Now, I have no discontinuities in the function G. Nothing that would indicate a discontinuity here. So I'm expecting this to be a nice, smooth, continuous function. And if I'm